Okay, let's get started. Good afternoon, everyone. Welcome to the Student Sensory Examiner series. My name is Zhang Li. I'll be the chair of today's talk, and I'm also one of the members in the student-led sensor interest research group. The primary aim of our group is to share research presentations in the area of sensors and sensing technologies. We hope the student seminar series will enable knowledge share and foster collaborations. Please visit our website in the bottom left corner to explore more about our organization. And if you would like to present your research or interested in joining our group, please do not hesitate to email us. The title of today's talk is Highly Sensitive Capacitive Pressure Sensor over a Wide Pressure Range Enabled by the Hybrid Responses of Highly Porous Nanocomposites. We're very excited to have Kyoung-Ho Ha here. Kyoung-Ho is a PhD candidate in the Mechanical Engineering Department at the University of Texas at Austin. He's working under the supervision of Professor Nanshu Lu, and he developed a soft pressure sensor that can be applicable for e-skin, robotic, and biosensors. His interdisciplinary research is across synthesizing composites, manufacturing porous structures and thin films, and analytical modeling. Before the talk begins, I would like to remind you that you can always ask questions at any time by using the chat box, and we'll collect the questions and ask the presenter at the end of the talk. Now I would like to hand over to Kyoung-Ho, and the time is yours.
Okay, thank you, Sang. Let me share my screen first. Okay. All right, good afternoon, everyone. I'm Kyoung-Ho, fifth year PhD student, working with Professor Nanshu Lu. Today, I'm going to give you a talk about highly sensitive capacitive pressure sensor over a wide pressure range enabled by the hybrid response of the porous nanocomposite. Measuring applied pressure on certain surfaces is important, and there are several types of soft pressure sensor. Among these, we have been focusing on capacitive pressure sensor because of its high sensitivity and high accuracy. In general, capacitive pressure sensors consist of two electrodes that sandwich a dielectric material. When you apply pressure to the sensor, capacitance increase with a decreasing gap between electrodes. The right plot is typical pressure response curve, and the sensitivity of the sensor is the slope of the curve. Based on our derivation, the theoretical initial sensitivity can be described as a function of K and E, where K is the dielectric constant and E is the compressive modulus of the dielectric material. So dielectric constant K and modulus E are key factors to increase sensitivity. There's been a lot of research to tune these parameters and make better pressure sensors. This is done by introducing an air layer inside of dielectric material. For example, micropatterns, foams, nanowire networks, fabrics, and spacers are used for generating air gap in a dielectric layer. Introducing air inside a dielectric lowers the compressive modulus E. You can think of sponge. Sponge is polymeric foam, and it's very easy to be compressed. Also, as we apply pressure, air goes out of the dielectric, and those air pockets are replaced by the dielectric material, which has higher dielectric constant than air. The dielectric constant change also increases sensitivity. To enlarge the K change, some studies focus on making a composite with a higher dielectric constant. Without the air, high K is useless because there's no change of the effective dielectric constant. So composites are used with porous structures. By doping or coating in the elastomer, composite can have higher dielectric constant and induce a high sensitivity of the sensor. These are sensitivities of other reported capacitive pressure sensors. Using air layers and high dielectric constant, people have improved the sensitivity of their pressure sensor. However, there is a trade-off relationship between sensitivity and pressure range. Also, improving pressure sensors by tuning air or dielectric constant have been thoroughly explored. So we want to see what other parameters we could explore to improve these devices. The new method we present is using piezo resistance and piezo capacitance at the same time. To do that, we fabricated a conductive porous nanocomposite, and the conductive nanocomposite is piezo-resistive, while the large number of open pores of the composite generates parasitic capacitance inside of the PNC. PNC means a porous nanocomposite. So there are piezo resistance and piezo capacitance in the PNC, and these hybrid response generate large impedance change of the PNC in response to pressure. Thus, we can improve the sensitivity more. We made this device capacitive by adding an ultra-thin insulating layer between PNC and one side of electrode. This is how we fabricate the PNC. Composite is made out of EcoFlex and function-light CNTs. The solution of CNT is sonicated to detach the CNT from each other. Due to high aspect ratio of the geometry of CNTs, they are entangled and make aggregates. Using ultrasonication, we can make a good dispersion of CNT, which is important for the conductivity of the PNC. And then we added EcoFlex, which is an uncured silicon rubbers to make a diluted nanocomposite. And a nickel foam is used as a template, and the nickel foam is dipped into the solution. As the composite is coated on the nickel foam template, we cure the composite by applying heat. And to remove the nickel foam, the samples are immersed in the hydrochloric acid. And finally, we can get a porous nanocomposite PNC with porosity of 86%. The left figure is illustration of sensor. We sandwich the conductive PNC with 2 electrodes and a PMMA dielectric layer. As I mentioned earlier, the sensor has hybrid responses that comes from its piezo-resistive and piezo-capacitive nature. So we call this sensor hybrid response pressure sensor, HRPS. The first plot is a resistance of PNC depending on the CNT doping ratio. CNT is a conductive nanomaterial, and as we can easily expect, as we dope more CNT, the resistance of the PNC decreases. Also, as pressure applied, the ligaments of the PNC contact each other and reduce the resistance of the PNC. Upper right plot is the capacitance change of the HRPS depending on the pressure. There's a monotonic trend of the capacitance change. As we dope more CNT, the HRPS shows a larger capacitance change. However, it's changed when we normalize the capacitance change by initial capacitance to calculate the sensitivity of the sensor. As the initial capacitance suddenly increases when CNT is doped more than 0.5%. When you see the final plot, the 0.5% CNT doped HRPS shows the highest sensitivity. This optimum doping condition is a unique property of the HRPS. To compare the performance of the HRPS with other conventionally engineered capacitive pressure sensors, 4 different dielectric materials are also fabricated, and these have only piezo capacitance. The basic material was a solid EcoFlex, and we add air gaps and/or doped CNT less than 0.2%, which makes the composite only highly dielectric but not conductive. So the first plot shows the stress strain curve of the 5 sensors. Regardless the CNT doping, the sensor with the foam structure has low compressive modulus than that with solid materials. The low compressive modulus is good for sensitivity of the sensors. And the lower plot shows capacitance change with pressure. Let's start off by looking at the pink curve at the bottom, which is a measurement of the pressure sensor made out of the pure Ecoflex. The low slope of the curve shows that this sensor has the lowest sensitivity. Next, on the light green curve, we add air gaps in the Ecoflex by making it a foam. This Ecoflex foam has a slightly higher sensitivity. We can take this one step further and dope the Ecoflex foam with carbon nanotube to make high dielectric constant, which is the dark green curve. And this gives us an even higher sensitivity than the other two samples. And finally, if we use conductive PNC with insulating layer, which is what is shown in the blue curve, we can make a pressure sensor with the highest sensitivity of all these samples. We also did some analytical modeling to verify this increasing trend in sensitivity that I showed in the previous graph. The upper left plot is for a sensor with a dielectric PNC, which shows that as dielectric constant K increase, the curve moves toward the left, which indicates higher sensitivity. For the conductive PNC at the bottom, we calculated the capacitance change depending on the resistance of the PNC. Unlike the dielectric PNC, sensor made using conductive PNC don't show a monotonic trend, but has optimal condition for the high sensitivity. You can see that among resistance from 1 mega ohm to 10 giga ohm, the 100 mega ohm, which is a medium condition in the range, has the steepest curve, which means the highest sensitivity. This existence of the optimal condition was also shown in the experimental result. This analytical calculation is compared with the experimental result and shows good agreement. In case where CNT is doped more than 0.5%, we can see a deviation between theoretical and experimental results. This is because when the composite is too conductive, electric field is changed, and the equivalent circuit we based on our model on doesn't accurately describe the system. Here, I compare the sensitivity of HARPS with other reported capacitive pressure sensors. We could achieve impressive improvement of the sensitivity over a wide pressure range, almost 423%. The thing I want to point out is the improvement is more significant in large pressure range, like above 10 kilopascal. This improvement at high pressure is because of the hybrid response of the PNC. The right plot shows sensitivity change rate, where I divided instantaneous sensitivity by initial sensitivity. So regardless the dielectric constant, the non-porous material shows drastic sensitivity drop as pressure increase here. When we add porosity, sensitivity drop is alleviated following L01. And by using the hybrid response, we can even increase the sensitivity change rate following L02. So in conclusion, by using hybrid response of PNC, we could achieve a larger sensitivity even at high pressure range. As a demonstration, I applied the subtle pressures, such as landing of Drosophila, blowing air, and dropping water droplets. The weight of the Drosophila was 0.7 milligram, which corresponds to 0.07 Pascal, and the Hertz was able to detect it. Another demonstration was measuring carotid arterial pulses under 1.5 kilopascal preload. To attach the Hertz on the neck, a medical dressing was used and generate the preload. Whether the subject is holding breath or not, the Hertz successfully measured the carotid arterial pulses with a preload. In this demonstration, a heart is located near the frontal artery under a VR headset. Although the headset applies the 8 kilopascal fluid, which is large, the sensor successfully monitors the temporal arterial pulses. Yeah, and that's pretty much it. And these are my supervisor, Dr. Lu, and my colleagues who work together regarding this project. And thank you very much.
Thank you so much for your amazing presentation. Let's wait a couple more of seconds for the audience to post their questions in the chat box. You can also unmute yourself and ask questions.
I have a question for Kyoung-Ho. Although I ask a lot of questions to him every day, I still have a question.
Okay.
So from the user's perspective, for end users, should they care about the absolute change or the relative change of capacitance?
They should consider the absolute capacitance change, because the relative capacitance change is for measuring the sensitivity of the pressure sensor, but sometimes it changes a lot depending on the initial capacitance. For example, when the initial capacitance change like just few picofarad, it could make a large change of relative capacitance change, but not for the absolute capacitance change. So for the user, they better to use the absolute capacitance change.
Then why, for the capacitive sensor papers, everyone talks about relative capacitance change?
That's simple, because only for removing the size effect. So for example, when we just compare the sensor performance based on the absolute capacitance change, larger capacitor will have large capacitance, and small capacitance will have a small capacitance, because the capacitance depends on the dimension of the dielectric material. So it's not unfair to compare them using the absolute capacitance change.
So in real application, the user should also take the area into consideration.
Sure.
It will be a balanced decision.
Right. Yeah, they should know the dimension of sensor.
Thank you.
We got another question from our audience. The question is, it seems that 1% of the CNTs increases the performance drastically, but have you found the limit? Perhaps if you increase the percentage of CNT even higher, how much better can you go? Would you saturate at some point?
Okay, I see. That's a really good question. So as you can see, if we throw more CNT inside the composite, the absolute capacitance change will increase. But there are two problems. One is the initial capacitance also increased. So because due to that, the relative capacitance change decreased. So that means the sensitivity is decreased. And another problem is about the fabrication process. So when we dope more CNT in the composite, the elastomer cannot be cured very well. So more than 1.5% CNT in the composite, some CNTs comes out, and so it's gonna be not ideal to be used for sensor. Saturate. Oh yeah, I think it should be saturate. Yeah, I think when the foam is very conductive, the resistance will be saturated, and the sensor performance also should be saturated.
Okay, due to the time constraint, thank you, Kyung-Ho, again for your great presentation. And if your question is not answered or you have further questions, please email us and we'll deliver your question to Kyung-Ho and get back to you soon. And I would like to introduce the next talk we'll have on 29th October. And our next talk is engineering bacterial transcription factors to sense poppy alkaloids, given by Simon. It will be held 2 weeks from today, and we're very much looking forward to seeing you again. Thank you.